Okay, so here we're going to be talking about latent heat. Latent heat is all to do with the energy involved with changing state from either a solid to a liquid or a liquid to a gas or vice versa. So this is not about the energy involved in changing an object's temperature. This is about the energy needed to change a substance from one state into another state. So to make a physical change take place, one of these reversible changes of states. Now there are two different situations we can look at: solid changing to a liquid, and back from a liquid to a solid. And when we're looking at that situation, we talk about the specific latent heat of fusion. And the definition for the specific latent heat of fusion is the amount of energy required to change the state of 1 kilogram of a solid to a liquid with no temperature change. So if we look at the equation here, we can see that the energy needed to do that is equal to the mass of the substance that you have times the specific latent heat of fusion. And that is a number that you would be given. You wouldn't be expected to know it. You could be expected to calculate it. But that's a number, a value that is specific for that substance changing from a solid to a liquid. Now, there are various different practical ways of finding this value. One of them is if you're using a joule meter, which is going to work out how much energy, electrical energy, is passed into this heater here. Okay, you could also use an ammeter and a voltmeter and use P equals IV. That would work as well. But what you've got here is you've got a heater heating up a known volume of ice, and then you're going to find out how much of that ice is melted and turned into water underneath. And by knowing the mass of the water that's been melted and measuring the energy that's been supplied to do that, then you can work out the specific latent heat of fusion. Now we can also define the specific latent heat of vaporization. So that involves changes of state from a liquid to a gas. The equation, as you can see here, is really similar. We've got the energy that's required is equal to the mass of the substance, so how many kilograms you've got, times the specific latent heat of vaporization. And the only reason that they're different equations is because quite often the latent heat of vaporization is a different value to the latent heat of fusion. So here's our definition for the specific latent heat of vaporization: the amount of energy required to change 1 kilogram of a substance from a liquid to a gas with no change in temperature. And again, we can measure this in the lab, this latent heat of vaporization. We can use a joule meter if we want to measure the energy, or again we can use an ammeter and a voltmeter and the time that it's running for. And then we've got that same heater we had before in a beaker of water that's been insulated, and you can have a think about why it's been insulated. It's on a top pan balance, and what happens is we heat up the water with a heater, and that will bring this liquid to the boil, and some of this liquid will then escape off as a gas, and as that happens the mass measured by the top pan balance will decrease. So you can measure the mass of the water that has been boiled and turned into a gas. So that's where you get your mass from the change in this reading here. Your joule meter will give the energy, and then you can calculate the latent heat of vaporization. Now if we tie this in with our graph that we saw before, remember whenever we see a new graph we look at the axes. Here this is a graph of temperature against time. So here we have got a substance that's been heated over time, and we've measured what happens to its temperature. And remember we said when we saw this graph before that while the substance is a solid, when it's heated its temperature will rise, but then when it reaches its melting point and you've got a solid turning into a liquid, there's no temperature change because the change of state is happening. at this point all the solid has changed into a liquid, and so the temperature begins to rise again until it reaches its boiling point. Here you have no temperature change as the substance changes state from a liquid into a solid, and then once all of the substance has changed into a gas, you can then get a temperature rise again. Now, what's important here is that we know which equation we can use for which part of the graph. So we've talked about specific heat capacity before, and we've said that the energy added to the system is equal to the mass of the substance you have times its specific heat capacity times the temperature change. So in this section of the graph here, where we're heating a solid, we'd use the specific heat capacity equation. Okay, we'd need to know how much of that solid we had, what its specific heat capacity was, that's a known value, and then what the temperature change is, so maybe from this temperature here to this temperature here. And then we could see how much energy had been added to the system over this section of the graph. Okay, same for this liquid section here. We would use the specific heat capacity equation to find out how much energy had been added to the system. We know the mass of the liquid, we know the specific heat capacity of it, and we know the temperature change. We can read that off from the graph from there to there. So this section of the graph, to find the total energy added, we'd use the specific heat capacity equation. And the same for this gas section here. We can measure the temperature change off the graph. We can be told the mass of gas, and we know its specific heat capacity. But what's interesting is that during these temperature changes we have to use the latent heat equations. Okay, so from here to here we've got no temperature change, so to calculate the energy added to the system here we just need the mass of the substance and the value for the latent heat, and then we can find out the energy added there. And the same for the latent heat of vaporization here. There's no temperature change, so we just need to know the mass of the substance and the latent heat of vaporization, and then we can work out the energy added to the system. Now this means that if you're given a question where they've asked you to calculate how much energy is required to change a solid, let's say at this temperature, into a liquid, let's say this temperature of 0 degrees C, we need to not just calculate the energy required to turn the solid, to raise the temperature of the solid up to 0 degrees C, we also have to calculate the energy needed to turn the solid into a liquid, because that requires energy. And that energy is our latent heat. Now, we can use this to explain all sorts of things. So one thing you might have heard of before is that a steam burn is worse than a liquid burn. And that's because if you're burnt by a liquid at its boiling point, let's say water at 100 degrees C, a certain amount of water at 100 degrees C contains a certain amount of energy. But if you had steam, which is a gas at the same temperature, that gas contains all of this extra heat here, and that heat is dissipated to your skin as the steam condenses on it, and so a steam burn transfers a lot more energy to your skin than a water burn was. So that's one common question that comes up when talking about latent heat. But again, really, really important to remember that to raise the temperature of something requires energy, but to change state requires energy as well, and we use different equations to do that. Now this is quite a good point to talk about what internal energy is. We first heard the term internal energy right at the beginning of Lower 5 when we were learning about our different types of energy, but now we're going to have a real think about what it is, what it means. So it's the total kinetic and potential energy of all the particles in a system. So if the particles can move around, if they're moving, those particles have kinetic energy. But also those particles can have potential energy, they can have the potential to do something. So when we heat up a substance, and we've got our heating graph here again, okay, when we heat it up, when we add energy, we're adding to the internal energy. We're giving that substance more internal energy. But we can see that internal energy doing two things. We could either see that the particles have been given more kinetic energy, And if that's the case, there'll be a rise in the temperature of the substance, okay? So if the particles have been given more kinetic energy, the temperature of the substance will rise as the substance has more internal energy. But you could also have that energy that's been added through heating be used to move the particles further apart from each other, and this would mean those particles have gained potential energy, and that's what happens when we have a change of state. Okay, so if we have a look at this graph here, this is a substance being heated from a solid into a gas. So as it's being heated, it gains internal energy, but different things are going on in terms of the type of internal energy, or specifically what's happening to the internal energy. So in this section here, where the solid is rising in temperature, the particles are being given more kinetic energy. During this section here, when we've got a change of state, the particles have gained more potential energy. This section here, where the liquid is rising in temperature, the particles have gained more kinetic energy. And this section here, where we've got a change in state, the particles have gained more potential energy. And then same for the gas, there's been a change in temperature, so the particles have more kinetic energy. Okay, so that's it. So let's see if this has all made sense and we can try a tricky exam style question. So let's have a look at this one. If you want to try it completely by yourself, you can just skip forward and look at the answers. If you want me to work through it with you, have a look at the next slides. So a cooker transfers energy to a pan of water at a rate of 600 watts. Once the water is boiling, the pan is heated for 5 minutes. The latent heat of vaporization of water is 2.5 megajoules per kilogram. The specific heat capacity of water is 4,200 joules per kilogram per degree C. The water started at 15 degrees C. I would like you to calculate the time taken to bring the water to the boil and the mass of water turned into a gas by boiling it for 5 minutes. So first of all, bug your question. Here you can see what I think are the important things that need bugging. And then write out your knowns, so they're all in one place, and your equations so that we know what we're working with. So here you can see I've got power, starting temperature. I've inferred, because they told me it was water, what the boiling point was. I've got 5 kilograms is my mass. I've got my time, 5 minutes, my latent heat of vaporization, and my specific heat capacity. First thing I need to do, check my units. Minutes is not going to be okay for this, so I convert minutes into seconds. Second of all, we've got megajoules here. That's no good either. Mega means 10 to the power of 6, so that's everything there in joules per kilogram. My 3 equations are power equals energy over time, energy equals the mass times the specific heat capacity times the temperature change, and energy equals the mass times the latent heat of vaporization. So, time to bring the water to the boil. My temperature change is from 15 to 100 degrees C, so that gives me a temperature change of 85 degrees C. I've got a mass of 5 kilograms of water and a specific heat capacity of 4,200 joules per kilograms per degree C. Using this specific heat capacity equation here, because I'm talking about a temperature change, not a change of state, I do 5 times 4,200 times 85, which gives me this. That's not enough though, because that just tells me the energy, and they wanted time. So when I use power equals energy over time, I can rearrange that. So energy over power equals time. I know my power was 600 watts, and so I get 2,975 seconds, which is quite a long time. So the second part of the question was what mass of water is turned into gas within the 5 minutes that it's boiling. So first of all, I've got to turn 5 minutes into seconds. I know the power and I know the latent heat of vaporization. So I've got 2 equations here, power equals energy over time, and energy equals mass times the latent heat of vaporization. So I rearrange my power equation here. So energy equals power times times, so 600 watts times 300 seconds gives me 180,000 joules. And then by rearranging my latent heat of vaporization equation, I then get the mass of the water being 0.072 kilograms. Now, if you wanted to challenge yourself even more, you could work out the volume of this water using your density equations, but I will leave that up to you.